Laws of exponents. We've already discussed what an exponent actually is. To refresh our memory, we know an exponent is made up of basically a base and a power. The base is what's being raised to that exponent. For instance, x squared, x is the base. An exponent of 2 tells you how many times the base is multiplied by itself. So x squared would be expanded out as x times x. Likewise, y to the 5th. That exponent 5 tells you the base y is multiplied by itself 5 times. Now each factor has its own exponent. So if you look at 2a cubed, that exponent of 3 only belongs to the a. The factor 2 out in front has its own exponent. If it's not shown, it's automatically 1. So therefore, when you expand it out, it becomes 2 times a times a times a. However, if you put parentheses around the 2 and the a, now everything inside the set of parentheses is being raised to the third power. In other words, the base is 2a. So you'd expand it out. The base 2a is multiplied by itself 3 times. And you do have to pay attention to parentheses. They're important. Some of the most common mistakes in math is students forget, or people forget to use parentheses when they should, or do not use them when they should. For instance, negative 3 squared is equal to negative 9. A lot of people think negative 3 squared without parentheses is equal to a positive 9, but anything negative is actually being multiplied by negative 1. So the exponent of 2 only belongs to the 3. So when you expand that out, it becomes negative 1 times 3, which is equal to negative 9. However, like I said, you put parentheses around the negative 3. Now the negative is being squared along with the 3. The base is negative 3, so it gets multiplied by itself. Negative 3 times negative 3 is equal to a positive 9. So watch those parentheses, pay attention to the details. Laws of exponents are basically the rules of exponents. What you can and cannot do with them, they're basically ways to simplify exponents. Most of them go by a name, but you usually don't have to know them by name, but you certainly have to recognize when and how to use each rule. The first one, the product rule. Product, of course, implies multiplication, so that's what's going on. We're multiplying 2 powers together that have the same base. So if you're multiplying 2 powers with the same base, you can simplify that by simply adding their exponents together. X to the nth times x to the nth simplifies to x to the n plus nth power. Notice the base did not change, you only add the exponents. So an example for that, given these 3 factors, r cubed times r to the 5th times t to the 7th, only one term made up of 3 factors. Only 2 of those 3 factors have like bases. So you're multiplying 2 powers with like bases, you add their exponents, becomes r to the 8th, and that t to the 7th just carries through. Example 2, the power rule. The power rule, a power is being raised to another power. For instance, x to the nth raised to the nth power. You simplify this by multiplying their exponents together. It becomes x raised to the n times nth power. In example 3, g to the 8th raised to the 7th. Once again, watch parentheses. That exponent of 7 only belongs to what's inside the set of parentheses, and what's in there is the g to the 8th, so a power raised to a power. You simplify that by multiplying the exponents. 8 times 7 is 56. That 3 basically you're not doing anything with, so it just carries through in the problem. Next we have the quotient rule. Quotient, of course, is division, so here we're dividing 2 powers with the same base. So in the quotient rule, if you're dividing 2 powers with the same base, you're going to subtract exponents. But order matters in subtraction. It's always going to be the numerator's exponent minus the denominator's exponent. So x to the nth over x to the nth simplifies to x to the n minus nth power. The numerator's exponent minus the denominator. So our example here, h to the 4th divided by h to the negative 3rd. The numerator's exponent 4 minus the denominator's exponent negative 3. Of course, 4 minus a negative 3 becomes 4 plus 3, or 7. So it simplifies to h to the 7th. Example 4, 0 exponent rule says anything raised to the 0 power is automatically equal to 1. It doesn't matter what that base is, it simplifies to 1. So let's take another look at example before we go any further, kind of putting a lot of these rules together. 5 times x to the negative 2nd times x squared raised to the 4th. So we need to simplify this, keeping in mind that we're not solving, we don't have an equation to solve, all we're doing is simplifying, so we follow the order of operations. Work what's inside the set of parentheses first, so what we have going on inside a set of parentheses is the multiplication of the two bases, or two powers with the same base. So product rule says we add those exponents together, negative 2 and a positive 2, of course, becomes 0. Still working what's inside the set of parentheses. Now we have an exponent of 0, which we know simplifies to just 1. So we've finished simplifying the parentheses. Next step in the order of operations, exponents. We have the exponent of 4. It only belongs to the 1. So 1 raised to the 4th power, of course, is just 1. And finally, the last step, order of operations, multiplication. 5 times 1 is just 5. The next rule, called the negative exponent rule. We never leave a negative exponent in our final answer. It's not considered simplified. So this rule shows us how to get rid of negative exponents. If you have a factor with a negative exponent in the numerator, you simply move it down to the denominator and that exponent becomes positive. Likewise, if you have a factor with a negative exponent already in the denominator, you move that factor up to the numerator and it becomes positive. You always want to wait to the very last step, or this is the very last thing you simplify. Use all your other rules, use the order of operation, and then at the very end, if you have any negative exponents left, use this rule to get rid of them. Because a lot of times just using some of the other rules will get rid of negative exponents for us, like this example we did a minute ago. We had a negative exponent, but that quotient rule got rid of it for us. So if you look at our example here, a to the negative 4th times b divided by c to the negative 7th. We cannot use the product rule in the numerator because we do not have like bases. Same reason we cannot use the quotient rule. We do not have any like bases. So the only thing we can do is get rid of negative exponents. That a to the 4th, negative 4th is going to be moved down to the denominator, giving us a positive 4 for an exponent. b is going to remain exactly where it's at in the numerator. B has an exponent of 1, which is fine. If we did move it down to the denominator, it would become a negative 1, which of course we do not want. And that c to the negative 7th, move that up to the numerator, it becomes a positive exponent 7. And the last rule or property is the distributed property for exponents. Now we've been using and working with the distributed property for multiplication. For instance, 2 times x plus 5, we know we have something out in front of a set of parentheses, we need to distribute or multiply everything inside by it, which of course in this case will give us 2x plus 10. However, now the distributed property for exponents. First of all, we have to determine if we can distribute an exponent. You can only distribute an exponent inside a set of parentheses if there's only one term inside that set of parentheses. In terms we know are separated by addition or subtraction, so if we do not have any addition or subtraction, that's only one term, which means we can distribute it. If we can distribute the exponent, we simply distribute it to each factor. So x divided by y is just one term with one factor, or excuse me, one term with two factors, so we distribute that n to each one of those two factors. Distribute to the x, distribute to the y. Our example here, 2a cubed over 5b to the 5th squared. Inside the set of parentheses, we do not have any addition or subtraction, so that's all one term, but it's one term made up of three factors. 2 is a factor, a cubed is a factor, b to the 5th is a factor. So we can distribute the exponent, and we're going to have to distribute to all three of those factors, giving us 2 squared, which is of course 4, a to the 6th, a power raised to a power. You multiply those exponents. 3 times 2 gives us 6. Same thing in the denominator, b to the 10th. Multiply those exponents. So example 1, simplify. So notice no equal sign. We do not have an equation. We're not solving. We're just simplifying. So follow the order of operations. Parentheses. We have two sets of parentheses. We cannot simplify anything inside the first set of parentheses. Likewise, we cannot simplify anything in the second set of parentheses. So we go on to exponents. The first set of parentheses has an exponent of 2. And since there's only one term inside that set of parentheses, we can distribute that exponent to everything inside. It's going to give us a to the negative 8th, b to the 2nd power, c to the 6th power, times the second set of parentheses being raised to the 3rd power. Since there's only one term, we can distribute it. 5 cubed, of course, is 125. A to the 18th, B to the negative 9th, and C to the 3rd. So we finish exponents. Now we go on to multiplication division. Of course, we do not have any division, but we certainly have multiplication, looking for like terms. So 125, we'll pull that out in front. It does not have a like term. We have A to the negative 8th and A to the 18th. Multiplying two powers with like bases, we add their exponents together. Becomes A to the 10th. B's, B squared, B to the negative 9th. Once again, multiplying two powers together with like bases, add their exponents. It becomes B to the negative 7th. And the C's, C to the 6th, C to the 3rd power, add their exponent, C to the 9th. Last step in the order of operations, addition and subtraction, which of course we do not have. So we simplified using the order of operations. The only thing left is to make sure we do not have any negative exponents, which of course we do. That B to the negative 7th. So now is when we want to get rid of them. At the very end, simply move that factor B to the negative 7th down to the denominator, and it becomes positive. Example 2, 4x plus 3 to the 7th times 4x plus 3 squared. Simplify order of operations. We cannot simplify anything inside the set of parentheses. Exponents, the first set of parentheses is being raised to the 7th power, but we cannot do anything with it. We cannot distribute it because we have two terms inside the set of parentheses. Same thing as the second set of parentheses. Two terms, we cannot distribute the exponent. So then we go on to multiplication. Well, these two sets of parentheses are being multiplied together, so basically we're multiplying two powers with like bases. The sets of parentheses are exactly the same, so the bases are the same, 4x plus 3, which means we can simply add their exponents together. So 4x plus 3 raised to the 9th power now is all the simplifying we can do. Example 3. Look at the problem, simplify, order of operations, no parentheses. We do not have really any exponents to work as far as distributing or anything, but we can neaten up or simplify that 4 squared a little bit. Obviously that becomes 16. So then we go on to multiplication division. So working left to right, obviously, we cannot do any multiplication, but division, look for like factors. The first pair of like factors, 16 over 6 reduces to 8 over 3. The next pair of like factors, m over m to the negative 8th, quotient rule, dividing two powers with like bases, subtract their exponent. So the numerator's exponent is 1 minus the denominator, so 1 minus a negative 8 becomes 1 plus 8, or 9. And the third pair of like factors, the n's, n to the 6th over n, or n to the first power, simplifies to n to the 5th. Subtract their exponents. We cannot simplify any further in the order of operations, and we do not have any negative exponents, so we're done. Example 4, simplify order of operations, no parentheses to work, no exponents at all to do anything with. Multiplication division, we cannot perform any of the multiplication, the numerator denominator, do not have any like bases, so we just go on to the division. First pair of like factors, 6 over 2, obviously becomes 3. The next factor, a to the negative 5th in the numerator, does not have a like factor, so we just carry it through. The b's, b to the negative 8th over b cubed, subtract. Negative 8 minus 3 gives us b to the negative 11th. And that factor d, d to the 7th, we can't do anything with, so it remains exactly where it's at in the denominator. No addition or subtraction, so we're done with the order of operations, but now we just have to simplify by getting rid of the negative exponents. Well, that 3 has its own exponent, positive 1, so it's not going to move, it's going to remain in the numerator. A to the negative 5th, move it down to the denominator, becomes an exponent of 5. B to the positive 11th, and of course D is already down there, we're not going to do anything with it. Another application of exponents is scientific notation. Scientific notation takes a number, any number, and puts it into one universal format, being a times 10 raised to the b power, where a, the number out in front, must be a number between 1 and 10, and b is simply going to be an integer as an exponent of 10. So we're going to convert a number into scientific notation and pull a number out of scientific notation. So you can see the technical steps for doing that, which honestly probably makes it a little more confusing than anything. As long as you understand what's going on in scientific notation, it pretty much walks you through each one of these. For instance, if I gave you all 3.2 times 10 to the positive second power 10 squared. Well, all this is a multiplication problem. First of all, we know 10 squared is 10 times 10, so basically we're taking 3.2 and multiplying it by 100. Well, if we multiply something by 100, it's going to get larger. So if 3.2 is going to become a larger number, we're going to move the decimal place 2 places to the right, which would become 320. If that would have been an exponent of negative 2, now we're multiplying by a decimal. So we'd move the decimal place 2 places to the left, 0.032. So example 1, 67,000. Convert that into scientific notation. Right now the decimal is behind the last 0, so there's only going to be one correct way to, or one correct place to move the decimal in order to make the number between 1 and 10. It has to go between the 6 and 7, giving us 6.7. Now all we do is count the number of places we moved the decimal. We moved it 1, 2, 3, 4 places, so that means our exponent for 10 is either going to be a negative 4 or a positive 4. Once again, just understanding the notation, right now we have 6.7. In order to get back to the original number, obviously 6.7 needs to be larger. So in order to make a number larger, we need to pull it out of scientific notation. It has to be a positive exponent. 6.7 times 10 to the 4th. Example 2. Right now the number is much smaller than 1, so in order to make the number between 1 and 10, move the decimal place between the 3 and the 4, 3.49. Now all we have to do is identify our value for b, 10's exponent. We move the decimal place 5 places. So if we were taking this number and putting it back into the original form, 3.49 obviously would have to get smaller, which means we'd have to multiply it by a decimal. So that has to be a negative 5 as 10's exponent. 3.49 times 10 to the negative 5th. Example 3. 7.09 is our value for a, where we need to move the decimal place between the 7 and the 0, making the number between 1 and 10. We moved it 3 places, and the exponent is going to be a positive 3. In order to take 7.09 and get back to our original value, it has to get larger, so therefore the exponent must be positive. Example 4, move the decimal place, make the number between 1 and 10, 1.04. We moved it 3 places to the right in this case. So in order to get back to our original value, convert 1.04 back into the, I'm not sure where I came up with 4 from, should be 5. But to get back to the original value, we'd have to move the decimal place 3 places to the right, in other words, multiply by a decimal. So therefore, 10's exponent is going to be a negative 3. So writing the number into scientific notation, and then converting the number back into standard form, taking the number out of scientific notation. Example 5, 5.67 times 10 to the negative 4, so we know we're going to move the decimal place 4 places. And since that exponent is a negative 4, that means our number 5.67 is going to get smaller. So in order to make that number smaller, we have to move the decimal place to the left. Move it to the left 4 places, giving us 0.000567. Example 6, 1.044 times 10 to the positive 6. Well, positive exponent means that number is going to get larger, so we're going to have to move the decimal place to the right in order to make 1.044 larger. Move it to the right 6 places. Multiplying and dividing numbers in scientific notation. Example 7 obviously has to multiply 2 numbers in scientific notation, which means the answer is going to be expected to be in scientific notation as well. What we could do is rewrite each number in standard form, multiply them together, and then write that answer in scientific notation. Or we can just multiply the numbers in scientific notation together. Begin by multiplying like factors. For instance, multiply their a values together. In this case, 4 times 3 gives us 12. Multiply their powers of 10 together. 10 to the 4th times 10 to the 7th. Multiplying two powers with like bases, we add their exponents, becomes 10 to the 11th. So we've done the multiplication. We have an answer in scientific notation, but it's not correct scientific notation. Our value for a now is greater than 10, so we just have to move the decimal place. One place to the left becoming 1.2, which of course is going to add 1 to 10's exponent. Add 1 to 11, giving us 12. Likewise, example 8, multiply these two numbers together, multiply their values for a. 6 and 8 gives us 48. Times 10 to the, multiply two powers with like bases, add their exponents, 10 to the 22nd power. Once again, since we multiply, their number is out in front now is too large, so move the decimal place in between the 4 and 8. 4.8 times 10 to the 23rd power.